All right. Season 2, Episode 6, Take 1. Welcome to Quantum Kinetics First Diffusion, Season 2, Episode 6. I'm here with...
Bryton Rodgers, Chief Production Officer of Quantum Kinetics Corporation.
Fantastic. It's great to have you back on the show, Bryton. Thanks for coming on. Real quick, just want to celebrate with you with our Strawberritas. 300,000 subscribers on YouTube. Thank you so much for joining in and following the First Diffusion movement here on planet Earth.
That's a heck of a milestone.
That is.
It wasn't too long ago that we were sitting around 50,000 followers, and I was like, all right, this is feeling pretty good. And then we hit 100, and then 250,000, now 300,000. That's a lot of people, man, that are tuning in and watching this.
Yeah, we're getting about like 800 subscribers a day, and they're from all around the world, and it seems like people are really excited about it. And we just launched our documentary last week. Mm-hmm. What do you think of that?
I thought it was fantastic. I really enjoyed that footage, and getting help filming that was a good move, I think. Yeah. What was your favorite part of the documentary? Oh, man. I really enjoyed getting to hear from Michael Leach and Randy Kent. I haven't had the opportunity to really talk to either of them yet, but I know that they were pretty important in the forming of this whole thing. Mm-hmm. And hearing a little bit from them, especially with their technical background, was pretty nice. Yeah, they were, you came in a little bit later, so you haven't really gotten to deal with them that much. They were more like founders and doing more of the research with us in the beginning. And if you guys haven't already, go ahead and check out the documentary. It'll be in the link description below. But so just to talk about the topics today, Bryton, I think we want to continue on with what is, just for the audience, like what is a nuclear reaction? Like what defines a nuclear reaction in fusion or fission? Well, this has come up a couple of times in the past, but it seems in the fission and fusion worlds, most people really only consider nuclear transmutation to be occurring based upon a pretty narrow signal of neutron flux. And it doesn't come up often, but this is something that's been a little bit of an impediment to more widespread acceptance of cold fusion, because cold fusion in a lot of these academic environments, something that they're missing frequently is fast neutron flux. Even so,
are you talking about low energy nuclear reactions, like not having fast neutrons?
Yeah. So there's metallic crystalline lattice induced fusion, where it's also called low energy nuclear reactions. And the reason that I'm confident that they have nuclear fusion going on is they measure using spectrography or other methods
electron microscopes.
Electron microscopy. Mm-hmm. They measure the presence of certain elements at the start in your sample and in your blank. And then after you've gone through this process to induce nuclear fusion, you measure it and you're like, wow, there's different elements here than when we started. That's kind of the origination of how we even knew that nuclear fission or fusion was a thing. Mm-hmm. Neutron flux, when we see this going on with the hot fusion industry and with fission, that is typically used as their indicator that they have fusion going on, but it's really a secondary effect. That's a measurement of how much the atomic contents of your sample material are changing. But if you can measure that the sample material is changing and you're not getting neutron flux, it's pretty obvious to anybody who's looking at this, at least in my opinion, that there's transmutation occurring. These nuclear cores of these atoms are changing.
Very small. They're very small. And that's
very small.
It's actually in this field of nuclear fusion, especially low energy nuclear reactions, also known as cold fusion. There are a lot of people working on this. And when you do a low nuclear energy reaction, the neutron flux is typically pretty mild, and there's actually a gradient, which most people don't realize, but there's a neutron flux gradient, and there are detectors that can detect these, and one of them is with Maximus Energy. You can go check him out. His website will be in the description. Dr. Maximus has made these detectors, and we have one of them right here. This is a gamma ray detector, which we've bought we have purchased 2 X-ray detectors from him, an SDD and a gamma ray and a helium-3 neutron detector. And in order to see nuclear, and from our science and our studies, is that when you turn on our reactors at low power, you do not see a neutron flux. And matter of fact, you don't even see really much of a gamma ray flux. It's very mild. But you do see a very strong X-ray flux from 1 keV all the way up to 20 keV on a regular basis.
Yep. And we can change that at will by adjusting the settings on our reactors.
Oh, yeah, the knob is...
And consistently keep it there without anything occurring that would indicate any sort of damage or wear on our reactors, or at least over the time periods we've measured.
Correct. When you're doing... The only economical nuclear fusion approach to industry standard is going to be a cold neutron flux. And that is like in the 1 electron volt neutron range, which again, those detectors are super hard. Like, to find that fidelity, that tightness, that small, weak neutron flux is really hard to detect. And that's why people in the academic community can so easily ridicule people doing low energy nuclear reactors, is because they say, you're not doing a nuclear flux, therefore you're not doing fusion, and these anomalies of transmutation are just anomalies. Mm-hmm. And they just write it all off. But that's actually not true. When you see transmutation, if you have a source and you don't see vanadium, you don't see, tungsten, you don't see copper, you don't see all these elements in the start. Nickel, exactly, nuclear fusion reactions. If you see them afterwards, you have done nuclear fusion for sure.
Especially if you can repeat that over and over and over again, like we can with our reactors.
And do you want to talk about how, like, if you turn the voltage to 30 to 60 to 90, like, there are changes in the transmutation?
Yeah, so our device accumulates low molecular weight or low atomic weight elements when we have a low input power.
So like a carbon, a nitrogen.
Carbon, nitrogen, oxygen, calcium, potassium, lithium, I think.
I think silicon is on there too.
Silicon's in the list.
Oh yeah, for sure.
But these things accumulate when we have it at a low power setting, and these are very... I'm saying power is a more general statement. We adjust it through other means.
Power is watts.
We're not really using more wattage input as we're adjusting this power setting up.
It's funny, Brett. It's funny if you have it at resonance just right, you can turn the voltage up and the amperage watts stays super duper low. It doesn't matter.
Yeah, which is really exciting.
Weird.
So we're using the same input cost if we're measuring by what you're getting off of the electrical grid, or from a battery, from a solar cell, but we can adjust the way we're stimulating the reactor, and we can get heavier stuff out like iron and nickel and
cobalt,
some more of these rare earth elements, which is pretty exciting because that's something that's
needed,
high value, and mining it from the environment and pulling it out of the Earth's crust is also a very
destructive.
Well, it's a destructive process. It's also very expensive equipment-wise. If this is something that can become a byproduct of our power generation or nuclear waste remediation industries, then this becomes a very, very useful
tool,
extra thing that we get out of these reactors, which is pretty exciting.
Yeah, like I said in the documentary, it's like basically only limited to the imagination you put it to work. So like if you want to mine for rare earth metal types that are basically hydrides, which by the way, hydrides are very important substances for energy generation. And they can only be made in particle accelerators that are super expensive and super bulky. And we use microparticle accelerators to induce this reaction, which is patented, trademarked, copyright protected, and research verified. So it is really our honor to tell the world about this technology, because it allows the world to now not be so worried about finite resources and finite this, finite that. No, we just use nuclear fusion, the proton to proton chain reaction that happens in the sun, to make elements that are useful for industry.
Which we've been talking about that all the way back to the first episode that I was on. I was saying, well, if you want some hard to get scarce resources, and you're in places where the setting up the industrial infrastructure to do big mining operations at significant scales is not an option, then that becomes fusion reactors like ours become an extremely useful tool. But again, to kind of finish off that point, even though we're not really using more power, as we adjust the settings on the resonance systems in the reactor, we can choose whether we're getting those heavier elements out of it as well.
If you take it to 90, if you go to 90 volts, then you'll see the uranium, you see the tungsten, you see the, those heavier elements.
Right.
And we've actually had gold show up, we've had silver show up. And I mean, remember, these are like really nanoparticulates, essentially, the electron scale, essentially. But there's another thing, too, that happens in terms of radioactive waste remediation with these cold neutron fluxes that we generate, is that it actually does fission at the same time.
Yeah, it's like it's picking a center point in the it's like our settings pick a specific range inside of that periodic table, and everything inside of that reactor starts coagulating or kind of falling into that range of atomic weights, and as it collects and settles out of the water in the reactor.
The technology is very similar to a sun, and I'll say it like this, Bryton. Most people don't know this, but the sun, our sun, during normal burning reactions of fusion, proton to proton chain reaction, we do not detect fast neutron radiation from our sun. Did you know that?
I've heard that before.
Interestingly enough, the only time we detect fast neutrons from our sun is when there's a solar flare. What?
Those solar flares sure resemble the fusion plasmas that we see in tokamak reactors and stellarators.
Yeah.
It's a large current loop with a self-confining plasma.
Yes.
And that's where you get these hot or really fast neutrons that we can detect.
And the thing about fast neutrons, which you guys probably do know, is that they destroy everything. They destroy the reactor walls, they embrittle it, they transmutate the shielding and turn it into radioactive waste, which then you have to decon later. These fast neutrons that these fast hot fusion reactors emit is not viable for a long-term commercial application, period. The only true commercialization application for nuclear fusion is with cold or resonant neutrons, which does not destroy the reactor. And there's a million things that I could talk about, but I'm sure you want us to probably move.
That's classified.
Well, speaking of classified, you want to talk about something interesting. That in 1875, there was a guy by the name of Rowland, and he was working closely with J.J. Thomson, who was the guy who discovered the electron, by the way. And Rowland came to J.J. Thomson and showed him an experiment and said, hey, if you take a disc like this, a piece of metal, and you put it on a motor and you spin it really fast at 3,660 RPM, that disc that's spinning super fast will start creating a magnetic field. There's no electricity in it. It's just spinning really fast metal. What? So you're saying there's current? Wait. Where is the magnetic fields only come from either electron dipoles being totally aligned or current flow in a wire. What? There's no current. It's just a spinning disk. Is there something that you may think that you could use that for, Bryton, maybe?
Well, that ties back to catastrophe theory that we've talked about before. When you start thinking of things in terms of fluid dynamics with a fluid ether, you can start making sense of a lot of these phenomena in a much more intuitive way. And then once you can make sense of these things in an intuitive way, you can start designing systems that utilize these effects. Because it is very much, it's like it scales. It doesn't have to operate just at the scale of an electron or a proton or neutron or an atom. You can make these things with the same geometries and just keep making them bigger.
Interestingly enough, James Clerk Maxwell, back in the 1860s, in his treatise, he said something along the same lines as that when you create a swirl, a vortex, he called it, a vortices, he called it, that
vortical motion.
Yeah.
I think I made that up earlier when we were chatting, but
I like it.
I like it. It fits.
It's that's where creativity comes, is where you take one idea and take another idea, and then you merge them together, and they become something that is useful.
I like to call it wordsmithing.
You would, you Viking.
I just need my hammer or axe or something.
You
just keep growing the beard out too. This thing's becoming a mess.
You're like Gimli from Lord of the Rings.
I'm not that short.
Oh, that's so funny. But yeah, so essentially going back to J.J. Thomson and Rowland, that the swirling action of the arc reactor. So in the way that the arc reactor is designed with the coils and the design of the electrodes, when you pulse this thing, it creates an artificial swirl that condenses the air, it condenses the water, it condenses maybe even the ether. And as it's doing that, it's emitting a plethora of X-rays. And we don't see, with our detectors, we don't see fast neutrons. We see cold neutrons. We see very soft gamma, just like a granite countertop. So this technology, you can stand by it and it's okay. As long as you're, about 3 feet away, you're fine. Right. Because the thing about X-rays, Bryton, is that when you have X-rays of this very low Bremsstrahlung type, they absorb rapidly in the air. Like absorb quickly.
Yeah.
Like most of the radiation is absorbed within 6 inches of the reactor.
And you've shown me that before with the X-ray detector, where you
can
hold
slide it away.
You turn the thing on, and we're sitting 3 feet away. I think you've got it sitting there.
You take this,
and you put it right up next to the reactor while it's running, and you're picking up pretty high counts. And then you just pull it back 6 inches away from the reactor, and just the air is so good at shielding against that it drops off precipitously. You get within about a foot away. You're not really getting appreciable amounts of X-ray radiation setting off that detector. So, which is a really interesting effect. I don't think that that's what most people think of when they think of X-rays. These are low energy X-rays. So when you think about the X-ray machines,
50,000 volts, and that'll hurt.
50,000
volt X-ray. That's
electric.
X-rays. Yeah, he's wordsmithing again.
It's been one of those days. I had a long drive to get here. All right.
Oh, yeah, that Seattle traffic in the morning, dude, in the rain is brutal, bro.
It's
brutal.
Rough. It's rough. Sometimes I get pretty lucky, but.
Well, we appreciate your efforts to teach the world about nuclear fusion and.
It's fun. I feel like I learn a lot by having these conversations too, just in the course of these podcasts. Sometimes I'll get a pretty good realization just in the creative act of speaking, and afterwards I'll be able to take that and inform some further theoretical discussion that we do later.
Absolutely.
This happens basically every time, and then I'll rewatch the video and I'm like, wow, I got a bunch of stuff out of that just by watching me speak about a topic. It's kind of a self-reinforcing circuit.
You know what Jason said about, because he comes on the podcast quite a bit too, is, what he said? He said that when he's, and I felt this as well, that when we do the podcasts, when we're done, like we close it off, we look at each other and go, what did we just talk about? I don't even remember what we said. Like, it's almost a euphoric kind of like this channeling energy through us to you guys about nuclear fusion.
It does feel like that. Yeah. It's a fun process, but worth it. Worth the drive every time.
Well, I appreciate you coming on, man. It's so fun to do these things with you. So is there anything else you want to discuss or talk about? Ether swirls, nuclear fusion, X-rays. By the way, there's a telescope in space called the Chandra Observatory.
This sounds familiar.
And this is what they use. It's not this exact one X-ray detector, but they have basically X-ray detectors on the Chandra Observatory that detect X-rays from black holes and stars and nebula and all that. They're not using it to detect gamma rays. They're not using it to detect neutrons.
Right.
These large body objects were pointing X-ray detectors, which, by the way, X-ray detectors are very new technology. This is new tech, by the way. It was basically hit the shelves in about 1991, 1993.
Oh, really? It was that late?
This is very
That's
new
pretty
tech,
cool.
guys. Like, this is why Fleischmann's and Pons had a really hard time proving that they were doing nuclear fusion, because they did it. They announced in 1989.
Yeah.
2 years later, this thing came out.
Yeah. Well,
Talk about bad timing.
Right. Real bad timing. Or, I mean, everything works out, I think, in the end. But the really exciting thing about that also is that the realization that this neutron flux is not critical to the action. We're not seeing fast neutron flux from the sun, except for those tiny events.
Only during the solar flares do we see the fast neutron flux, which is the audience, if they're going to take anything away from this episode, is that they need to understand that the nuclear fusion of our sun is very cool. It's cold. It's cold nuclear fusion. When a solar flare hits, that's when you see fast neutrons. So these are things that you all need to understand, that when someone says on a comment, like in our comment section, that says poo-poo this, poo-poo that, it's not true, you need to understand that those people are super ignorant and they're just angry. And what we're trying to tell you is that there's a new way to do nuclear fusion. It's amazing, it's fun, it's easy, and it's going to change your world as long as you get behind it. If you don't get behind this, there's nothing we can do to help you.
Right. It's more than just a quantum kinetics team effort. This takes people talking about it to really bring enough attention to this exciting technology, and enough, even like, we welcome critical eyes too. Like, we want to have the conversations with people asking the tough questions, because unless we're able to answer those tough questions, we're not going to get the chance to address it and bring over a few more new allies each time one of those gets answered.
Well, I'll tell you that I'm not going to disclose anything, but it looks like there may be some allies coming forward. So we're very thrilled about that, because this technology can do everything that we say it can do and more. There are things that we do not disclose to the public because it is just so awesome.
Yeah. The amount of stuff waiting for us to be working on prototyping a lot of things at once is enormous.
It is. Oh, and by the way, just to do a little bit of a shift of the conversation, we did just hit 300 or 3,000 watchtowers on our on our YouTube channel. So we're now in the YouTube partnership program. Cheers.
Cheers to that.
And everyone should become a partner or join up and be a member, because you get your little stickers and your badges and all that. So go ahead and support the cold nuclear fusion movement by becoming a member of Quantum Kinetics YouTube channel.
There's some cool merch coming down the pipeline. We at least have a really cool symbol or logo.
Yeah. I was showing you some of the templates for that, and the merch will be coming out soon, so you guys can check that out. Actually, we'll go ahead and put the link for spring in the link description for you guys. So, but do you have any other questions, thoughts for today's podcast, Bryton? Anything that you want to talk about, for real?
Well, I do like talking about the topic of radiation in general because that does become important. I think a little bit of a debrief, or not a debrief, refresher course for everybody would be of help. Mm-hmm. So what you see in nuclear radiation comes down to alpha particles, which are basically helium. Mm-hmm. They're helium cores shooting out, and those are pretty low penetration. They don't really go very far.
They'll bounce off a shirt or your skin. They'll bounce
off a piece of paper. Mm-hmm. And then you have your beta radiation, which are electrons. They're just shooting off, right?
They're quanta. We'll just call them quanta because it's a transition between an electron and an X-ray photon. Okay. A beta particle is.
So what we'll say electrons.
High energy
with
particle.
Air quotes on it, but it's a fairly high energy particle, and those are a little bit more penetrating, but not as high as the gamma radiation.
Which is
which we have a little detector right here for.
Actually, let's do a demo real quick.
Yeah, here, let's do a quick little demo.
So you want to get that cesium out?
Yeah.
Let's
give credit.
Yeah, so here's the thing. Check this out. This is Maximus's pulse counter technology. And the thing about most detectors, like radiation detectors, is they just do counts. Right. What the cool thing about Maximus's technology is that it doesn't just do counts, it does intensity, right? It'll do like an actual graph. So we'll go ahead and start the picoscope.
And we'll show off the little cesium sample here.
And which is really interesting that most people don't realize is that literally the background radiation of gamma is low.
It's pointed towards you right now, so away from the sample. Yeah. So it's still picking up stuff.
What this is picking up is just background radiation. And it's very cool because you can see the spectrum of the radiation. So I'm going to bring this over to you, and you can put the cesium.
How good's our view from
here?
I'll hold this up.
I'll do the cesium.
And you hold up the cesium.
So you can see that there's a spike now. See that? Cesium emission spike. And then I'll pull it away, and then it goes away. Look at the histogram. It goes away. See, it drops out.
Yeah.
So there's that. So this is the kind of technology you need. And by the way, Maximus has done an amazing job on his detectors. His software packages give you the ability to do full systems monitoring and full systems modification to like get that fidelity of that aperture just right so that you're not getting too much background radiation and not oversaturating the system. Right. So if you're going to be doing nuclear fusion studies, you have to use Dr. Maximus's detectors. It's just they're best in the world right now.
The real special detectors that he has, right? The real claim to fame is the helium-3 neutron detector, correct?
Yeah, we have that one. It is a huge, bulky thing. It's funny. The first thing I ever bought from Maximus was the neutron detector. And I bought the neutron detector and the gamma ray detector at the same time because I was like, oh, well, we think it might be nuclear. We're going to need neutron detectors, right? Because that's what I thought originally, because that's what everyone thinks.
Yeah.
And so we put the neutron detector in front of the reactor, turned it on, and turned it up, and nothing was happening. And then I was like, you know what, I'm going to turn it up all the way. And I turned it up all the way, and boom, then you start seeing like, thermal neutrons and like a little bit warmer neutrons, right?
Right.
So, and then I was like, well, okay, so essentially, do I need another detector? So I went back on his website and was like, I saw he had an X-ray detector. And I was like, oh my gosh, I should buy that too. So we've spent here at Quantum Kinetics a pretty good coin getting all these detectors. And without a doubt, the best, if you're going to be doing low energy nuclear reaction testing and studies, you have to have an X-ray detector. Because you know why? It's astronomy. Astronomy uses this to detect black holes, nebula, fusion events, cold neutron events, because it's the X-rays that you see. It's very important to understand the difference. That this is cold neutron stuff, not hot, fast neutrons.
And those fast neutrons can travel enormous distances through highly dense materials and all kinds of stuff, but these cold neutrons don't really travel anywhere. You've referred to them as resonant neutrons, but basically what seems to be going on from my perspective, you've had a little bit more time thinking about this one, obviously. These resonant systems are essentially, as it's forming these heavier elements within this space and forming electron-positron pairs and forming more protons and forming more neutrons. These neutrons are basically just being held in that space. They're not escaping. So we're actually able to, because of that lack of escaping high energy neutrons, they're staying there. So it's actually seems like what is going on is a much more efficient neutron capture event to grow these atomic nuclei. Feel free to pick that apart or not. But it seems to me likely that that's what's happening here.
That's right on the money, because what happens is just like the X-rays of this low energy X-ray from 1 to 20 keV, those X-rays are absorbed rapidly by other electrons in the area, in the air, in the water, in the vacuum of space, or whatever. And these neutrons that we create, think of it like a cold neutron is like love. If someone's being nice to you, you want to hang out with them. It's like someone's giving you compliments, or someone's blowing you kisses, or like, hey, let's talk. Like, you're attracted to that. And so these neutron fluxes generate and create this like kind of love attraction.
Gravity.
Thank you.
We're getting there.
You put words in my mouth. It's true. But then the fast neutrons, unfortunately, fast neutrons are like angry Nazis. They're just full of hate. They just don't like anything. They're like, I don't like this. I don't like that. My teeth hurt. My hair's bad. Like, they're just angry little suckers, right? Like, fast neutrons are like, just make them go away. Like,
they're
don't use them.
Starting fights.
Yes.
That's where all that transmutation of the secondary materials in your typical hot fusion reactor is coming from. They're shooting out. They don't have really as direct of a barrier to motion, but they're moving fast enough that they smash around and they change your steel pipe or pressure vessel or your insulating material or your concrete shielding wall outside of that into a plethora of elements that are not what you started with, and a decent portion of those are unstable, and so they're radioactive. So it turns not only your equipment but your shielding materials over long periods of operation. It turns those into radioactive materials themselves.
Those fast neutrons do that, yeah.
Which over the long term is definitely a huge technical problem for the hot fusion industry. And
even thorium salt reactors will have that problem.
Right. So even as they bump these operation timelines up, where I think they're up to 20 or 30 minutes, somewhere in that range right now for the longest runtime.
The Stellarator broke 22 minutes, but the Tokamak is still stuck at 22 minutes.
Okay. So ballparking it, even as they try to push that up further by improving their materials and other engineering factors, they're going to be increasingly dealing with the radioactively active
poisoning
materials. Basically, poisoning the materials of the equipment over long term, and that is it's a potential safety concern, but I think we know how to deal with radioactive waste, but it creates another additional pipeline of waste that we have to contend with and store safely and spend enormous amounts of money maintaining these stockpiles of various radioactive materials that we may or may not know what to do with.
You know what's funny about the Tokamak? If you look inside the Tokamak reactor, they look like bricks, stainless steel bricks that are all around, and they're held together with like bolts.
Okay.
and the bolts, you can undo the bolts and take away.
Yeah.
And that's what they do. They take away the wall and they put in a new one in.
Yeah.
And then they put in a screw.
They're replacing
They
the
just
material.
replaced the block that just got radiated.
Right.
And now it's burnt. It's burnt, 1. It's poisoned, 2. And 3, it's scorched. And actually, there's sometimes when there's a dead short, they call it a una arc. There's these una arcs that happen inside these tokamaks, and these una arcs they like basically blow off part of the chunks of the material of the reactor.
Yeah, well, that's the destructive operation that we've talked about before, right?
Yeah.
Yeah, these things require, from what my understanding, these require significant rebuilding each time they run it.
Yeah, and we don't have any of those problems here at Quantum Kinetics with the ARC reactor fusion on demand technology. I mean, we literally are running the reactor we've been running it for a year now, almost like 10 months. And it's just cooking away on water, and it's just truth is stranger.
Continuous operation for 10 months. That's commercializable.
I kind of want to say something, but I'm going to say it. Okay, we were talking about hot fusion, how it destroys the bricks, and they have to pull them out and put in new ones. Okay, here's the weird thing about cold nuclear fusion, is that the sediment buildup that occurs on the electrodes actually aids into the new fusion. It's like
it seems to accelerate the sedimentation occurring. So as there's more sediment in the reactor, more sediment is forming faster.
Something's growing.
Yeah.
What is it? What's growing?
It's almost like it's a living thing. It's a really, really cool thing to watch.
I'm telling you, man, like cold nuclear fusion, it's just love. Period. Hot fusion is not love. It's like angry. It's madness. It's madness, man. Right. So, but
they've got a lot of challenges that we don't have.
Right. Yeah, we're ready to deploy right now. Essentially, we got the wine. We're just looking for some bread. You know what I'm saying? Let's go party.
Right.
So, but. All right, so that we beat the horse dead on that one with the hot fusion.
We did. I think we got very narrow on this one. Sometimes it feels like it needs to happen, though.
Yeah,
and I think these are important topics. It's not with any malice in the heart. It's just recognizing and calling out some things where we see some potential issues, and we think we have a way to work around that, and we're excited for when people come to us looking for help and assistance or cooperation. It's a team effort here.
Yeah, it's again, like I kind of mentioned this like about 10 minutes ago, that essentially this technology goes nowhere if you guys don't do anything, right? Like we have spent tons of money and tons of time to get it legalized, to get it research verified, to get it to a maturity level for you. Now the baton is yours. Like if you were doing a 4x1 relay and track, like back in high school.
Yeah.
Which
those were the days.
Those were the days. Okay, when you did track, did you ever do the 4x1? Did they put you in that?
I did the 4x4.
Oh, brutal, bro.
That was brutal.
What leg were you?
Oh, I think I did second or third most of the time.
Oh, so you were the slow guy, huh?
Yeah, I was the slow guy. I was not the speedy guy.
Yeah, they put me on third leg, so I was the slowest. It's because I was the shortest, but anyway. Yeah, so essentially the baton is now yours. Like that's our job. Like we've done what we can for you guys, and so we're ready to help if you guys want help. And this world that this technology can bring forward is absolutely stunning. It's going to make the earth happier. It's going to make the whales happier. It's going to make the plankton happier. It's going to make the birds and the trees happier. It's going to make you have a healthier life. The things that this technology can do is only limited to the imagination. And I know that sounds strange for most people, and they're like, no, this can't be. I don't believe it. There's only one way to do it, and it's hot fusion, blah, blah. No, I'm sorry. Mother Nature just does what she does. either you learn her method or we're all going to perish. It's that simple. And I don't mean to be bleak, but it's the truth. So let's rock and roll and let's get this going.
And get to the space age, baby.
Well, and that's something I want to talk about with, and actually, let's go ahead and talk a little bit about that. Not a lot, but let's just, because we did mention the spinning top metal that makes current. Let's just hit on this before we end about the future of what this technology can do.
A little bit of a teaser.
Just a teaser, yeah. When you have an electronic circuit that you pull the switch and it closes the circuit, there is an impulse of electricity that happens, but there's no current yet. There's a delay. There's a very small delay.
The voltage propagates
instantly, almost
instantly through a circuit.
And I would say it's pretty dang close to almost.
As close as we can reasonably say instant is, right?
But then...
we have measurement limitations, right?
Correct. But then once the impulse happens in the wire, there is this... And by the way, this is true. The ether or the energy around the wire, the dielectric, like, for example, if you have a wire and there's water around the wire and you dead short it, the current will build up slower. If you have air around it, it'll build up faster. It depends on the dielectric around the wire.
The insulator affects the voltage and current properties of the conductor.
Correct. So what that tells you...
Or the circuit. Let's call it a circuit because it requires both.
Yes. And this is exactly what Oliver Heaviside, James Clerk Maxwell, and Michael Faraday were talking about way back in the 1880s, is that literally the ether is being pushed into the wire because where does the current start? On the skin effect, on the outside of the wire. The electrons begin to migrate on the outside first. Why? Because there's a pushing in.
Hell of a question to end on.
And if your spaceship was one giant conductor,
yeah,
let's just end on that.
Okay.
Because the Alcubierre, how do you say that? Alcubierre drives or whatever, those warp core drives, the space going down and the space going up behind the craft, you know.
I have no idea what those are called, but I've seen those diagrams pulled out from some mysterious source just floating around on the internet so many times just when I'm cruising around YouTube in the evening.
Checking out our YouTube channel, I'm sure.
Exactly. Watching Quantum Kinetics on loop. Do it.
Yes, absolutely. Actually, the more you guys learn, the more you'll be able to pick up what we're saying, because we're actually we're like leading breadcrumbs for you guys. Like, we already know a lot more than what we talk about, by the way.
There's some layers to these discussions where I certainly, even though we've done a lot of theoretical discussion talking about this stuff, when we talk about what we choose to present in these podcasts, when I go back and watch again, I get more out of it.
Mm-hmm. Oh yeah.
But that has to be coupled with actual like hard work and study and thinking about it and effort. It takes time for these things to absorb into the brain. You mean
the voltage push behind you to make you do it?
Yeah. You got to apply some voltage to this effort, and it's a really fun process to learn this stuff. And I encourage everybody watching to do a bit of their own. Yeah. I think you'll get more out of these podcasts if you do.
Yeah, absolutely. So, well, thank you so much for coming on the show once again, Bryton. It's always a pleasure to have you. And
always a pleasure to be here.
Yeah, we're really excited about the next chapters of Quantum Kinetics, because this technology is really going to make everyone's world a lot better. And with that being said, I think we'll go ahead and close it up today, Bryton.
Adieu.
All right, adieu. Thank you so much for tuning in, and we will see you guys on the next one. I believe Jason McCoy is coming up on the next one. Don't quote me on that, but I think we're going to be talking about the future of what actual cold nuclear fusion industries will look like, and we'll have visual aids as well. So it'd be very exciting.
And that's a fun one. And we're kicking around the idea of bringing on some guests in the near future too, aren't we?
Yes.
Not fully decided yet on timing, but it's coming in.
Well, we've got 2 people that want to come on the show, but we have to kind of schedule that and get all the intricacies together. But it's interesting how people are like, I want to be on the show too.
It's fun. It's fun. Like, I'm sure there's plenty of people out there watching this and going like, oh, that's not how it is. But it's a fun show, and I think we bring up a lot of really valid questions and points, even if you don't immediately agree with the things we're saying. And I certainly agree with what I'm saying.
Yeah, of course you do. Well, you know what I love?
You kind of have to, right?
You know what I love? Like, every time we do something and you watch what's going on the internet, someone says something super duper similar to what we just said on the last podcast. Like,
that's been a lot of fun. That's been a lot of fun. I'm so excited when I say some of this stuff that I've been thinking about and talking about for a few years now. Mm-hmm. And suddenly the next week I'm watching podcasts and videos from other channels. I'm like, I really like this channel. I'm so excited that they're also talking about this stuff at the same time.
Absolutely.
A little bit of
negative energy, negative light.
A little bit of coincidence and cooperation and resonance on a larger scale. I think we're working in a good direction with this stuff.
Yeah, we like to collaborate too, if whoever wants to, and it's going to be really exciting. I mean, this whole movement, guys, is just freaking awesome. You don't want to miss it. This is going to be the story of the century, so you need to join in, subscribe, watch, like, share, and subscribe, man. Become a member, because this is a massive wave that is about ready to crest over.
Fun times.
All right, we'll see you guys on the next one. Thanks for tuning in, and take care of yourselves.
Take care.
Thanks, Bryton.